3.3 that we're going to talk about, I'm discussing now. So there's a certain amount of stuff in 7.3 that we don't really need. I'm going kind of quickly and picking out just stuff that we need from this chapter, because we could spend a lot of time here, but we won't get a lot of rewards. So we're moving quickly. So here we're treating the important case where the sampling distribution is normal, which wasn't the case in this previous example here, where because we were drawing just two, the central limit theorem doesn't really kick in. So, but here we're going to assume that our sampling distribution is normal, and so we have a population of 393 hospitals. Xi is the number of patients discharged from the ith hospital in a certain year, and we're told that the mean and the standard deviation is 814.6 and 590, and a simple random sample of size 50 is taken. So we have this picture here, and we're asked to basically find what's the chance that, let's say that the chance that we're more than 100 away from the mean, which would mean we are outside, we're either less than 714.6 or greater than 914.6. So this is the sampling distribution. It's normally distributed here by the central limit theorem. The standard error is given by this formula. Again, this is something we will prove a little bit later, that this is the standard error for this estimator x bar. So just we'll take that on faith at the moment, and so we can see that this is 77.95, and so to find this area here, we just normalize in a usual way, put it into standard normal. Phi here is the CDF, so we are just basically calculating the area using a CDF or a lookup table, or you can use R. So that finishes that. In this situation, our box here has lots of different numbers in it, lots of different valued numbers. In the dichotomous case, you have just zeros and ones. In this particular example, a hospital has fewer than 1,000 discharges or not, and we're told that proportion is 0.65. Okay. And so I asked you then to find the probability that that your sampling distribution is more than 0.13 away from 0.65. So in other words, this shaded region in the tails here, we find the standard error in the same way, and we compute this probability in exactly the same way as before. You're all getting tired at this point, but I showed no mercy, and we just continued on to discuss confidence intervals. So this is really a sort of a theoretical construction here, and what we're doing is we're setting alpha, which is going to be our level of significance, some number between 0 and 1. So for example, if you're looking for a 95% confidence interval, alpha then would be 0.05. Z alpha, which is sometimes written Z sub alpha, I'm being a little bit inconsistent in my notation, and I can't quite remember what the book uses here. But in any case, Z alpha is the number such that the area under the standard normal curve to the right of Z alpha is alpha. So right now my screen seems to have frozen. Okay, let me just bear with me for a second. That's rather strange. So for some reason I drew this curve here which isn't normal looking, so I'm actually going to redraw that. Again, bear with me for a second. This should be a normal curve. Okay, and Z alpha is the area to the right. So this area here is alpha, and this area here is 1 minus alpha. Okay, so the probability that you're between, the probability under the standard normal curve that you're between Z alpha over 2 and minus Z alpha over 2 and Z alpha over 2, in other words, the chance that you are in here, is clearly 1 minus alpha. So, so as an example, if alpha is 0.05, you can verify using R that these cutoffs here are plus or minus 1.96. Okay, so we're constructing the confidence interval. We're constructing a confidence interval here, and Z is x bar minus mu over sigma x bar. And we just do some basic algebraic manipulations here to find that the probability that mu is in this interval here. So this probability is called a 1 minus alpha times 100% confidence interval of mu. And I somehow forgot to mention that this is 1 minus alpha, right? So just by construction, right? The chance that we're in this highlighted region here is 1 minus alpha. But all of these are equivalent, and this interval here is the 1 minus alpha times 100% confidence interval. And the important interpretation of this, I think, is best highlighted here, where you can see that if 80 is your parameter of, let's say you have a box with 80% red marbles. So if you were to, we're showing here 100 confidence intervals. 100 confidence intervals, let's say 195% confidence intervals for this parameter, and there's a 95% chance that your confidence interval contains the true parameter, and a 5% chance that it doesn't. So there's winners and losers, and that's the main interpretation of a confidence interval. 95% chance that your confidence interval contains the true population parameter. And then, just as you were completely exhausted and ready to leave, I told you that you should please review this derivation, something that we'll use, and it basically shows that the sample variance is an unbiased estimator for the population variance. And I think this is very straightforward. derivation here, just using basic properties about expectations and definition of variance. I don't really have much to say here, just follow all the steps and you'll see that, you'll see kind of surprisingly that there's a n-1 here, which is why the sample variance, why we put a n-1 in the denominator is because we want the expectation of s squared to be sigma squared. And so this is an important result. And that was the first day. It was a pleasure to meet all of you, and I'll see you bright and early tomorrow.